Hello, my name is Anna Wiles, and this is my Physics 2211 Lab 1 Constant Velocity video. So here's the introduction. This lab explores how Newton's second law, which is force equals mass times acceleration, explains an object's motion. The key ideas here are constant velocity, which is constant speed in a constant direction, with a net force of 0. The momentum principle, which is the change in momentum of an object is equal to the net force acting on the object times the duration of the interaction. And the system here, which is the ping pong ball, and the surroundings are everything else, the push force, friction, gravity, etc. The change was that the ball was pushed and it moves at a constant velocity to the right. The formulas that we use are the velocity update formula, which is final velocity equals initial velocity plus F net over m times delta t, and the position update formula, which is final position equals initial position plus average velocity times delta t. And so here I'm just showing how I found the initial velocity. I used velocity equals change in position over change in time, and you can just see some of my data plugged in using the first 2 points in my tracker data. So moving into tracker, here is what my experiment looked like. So as you can see, I pushed a ping pong ball to the right. I have 18 data points here starting at the origin 0, 0. And here is a preview of what my graph looks like. And then moving into GlowScript, here is my code. So I set the mass to be equal the mass of a ping pong ball, so 0.0027 kilograms. The initial position was the vector 0, 0, 0. And then as I showed in the first slide, the initial velocity that I got was 0.554 meters per second. And so this is the velocity that I used for the computational model. My time started at 0, and my delta t was 0.033 seconds. So I changed the t here to be 0.7 because my video was pretty short. And then here you can see the two formulas that we were using, the velocity update and the position update. And so now we're just going to run the program. And as you can see, the ball moves pretty quickly to the right, matches the movement of the ping pong ball. And here's the position versus time graph. As you can see, it's linear, it's increasing, and then the velocity versus time graph is constant because the net force is 0, so the velocity is constant. And so here is the graph comparing the tracker data, which is the red dots, and the GlowScript data, which are blue. As you can see, here are my data points for both. And the data for the tracker and GlowScript is matching up originally in the graph, but then it starts to move farther apart. So the observations. The experimental model is not linear, and this is due to error in getting the ping pong ball to move at a constant speed in a straight line. However, it is very close to being correct, and the points match in the beginning because I used the first 2 data points in the tracker to create the velocity for the GlowScript data. So that's why they match in the beginning, but then the ping pong ball was not moving in a fully constant velocity, so it starts to level out just a little bit. What if the axes were flipped? Then the ping pong ball would instead be shown as moving in negative x and or negative y directions, example to the left instead of to the right. And then what does it mean? Is it possible to know how many forces were necessary to make the net force 0? Not really. It's pretty clear that the net force in the experiment was not exactly 0, and this is because humans are only so precise. This would be easier to track if the experiment was done by machines, and that way the actual velocity would be constant. Thanks for watching.